Deep within the velvet silence of the constellation Libra, a single pale spark drifts through the abyss, unremarkable to the naked eye and hidden amongst a sea of younger, more arrogant suns. This is HD 140,283. To a casual observer it appears as a mere pinprick of light, yet it carries within its cooling plasma a secret capable of dismantling the very architecture of modern chronology. It is a wanderer, a celestial nomad that has spent eons traversing the outskirts of the Milky Way, moving like a ghost through the galactic halo. While the spiral arms of our galaxy churn with the birth of new stars and the violent deaths of massive giants, this unassuming object glides through the darkness with the steady rhythmic pulse of a survivor from a forgotten era. It does not belong to the neighbourhood of the sun. It is a visitor from the deep past, a relic of a time when the cosmos was fundamentally different from the one we inhabit today. The journey of this star has been one of immense loneliness and staggering duration. It shears through the gravitational tides of the Milky Way at a velocity that defies the local logic of the heavens, a speedster born from the chaotic gravitational dances of the early universe. As it cuts through the local interstellar medium, it leaves no wake, only the silent testimony of its ancient composition. For decades, astronomers catalogued it as just another high-velocity star, a curious but ultimately minor detail in the grand map of the sky. However, as the tools of observation sharpened and the mathematics of stellar evolution matured, the true nature of this object began to emerge from the shadows. It was not merely old, it was ancient in a way that defied the laws of the universe itself. This star has earned a name that resonates with the weight of millennia, Methuselah. In the ancient lore of humanity, Methuselah was the man who outlived all others, a figure of such extreme longevity that his life spanned the gap between worlds. In the realm of astrophysics, the name is even more hauntingly appropriate. For a terrifying interval in the history of science, the calculations derived from the light of this star suggested an age of 16 billion years. This figure did not merely challenge our understanding of stellar physics, it threatened to incinerate the very foundation of cosmology. If the universe itself began in a singular explosive event 13.8 billion years ago, then a star 16 billion years old is a mathematical ghost. It is an impossible object, a guest who arrived at the party before the house was even built. It is a witness to a dawn that, according to our most sacred equations, had not yet occurred. The existence of Methuselah presented a crisis of reality. We found ourselves staring into the face of a paradox where the child was older than the parent. The light arriving from HD 140,283 travelled across the void to tell us that our calendar of the cosmos was a house of cards. It forced a confrontation between the macroscopic laws that govern the expansion of space and the microscopic laws that govern the burning of a star's heart. If the star was correct, then the Big Bang was a lie, or at least a truth so poorly understood that we had missed the mark by billions of years. If the Big Bang was correct, then our understanding of how a star lives and dies was fundamentally broken. There was no middle ground, only the cold, hard light of an ancient sun that refused to fit within the boundaries of human logic. This pale spark, drifting so quietly through the scales of Libra, became the ultimate arbiter of truth. It sat at the intersection of two conflicting versions of history, a silent sentinel demanding that we reconcile the age of the heavens with the age of the objects within them. To look upon Methuselah is to look upon the very first moments of creation, to a period when the first light was just beginning to pierce the primordial fog of the Dark Ages. It is a bridge between the chaotic, hydrogen-rich aftermath of the beginning and the structured, metal-heavy reality of the present. Its presence suggests that we are missing a fundamental piece of the physics puzzle, a hidden variable in the equations of the very first moments of time. As it wanders the halo of our galaxy, Methuselah serves as a mirror reflecting our own ignorance and our relentless, burning desire to know the truth of our origins. We are the children of the stars looking back through the telescope of time at our own ancestors, trying to understand how a single ball of plasma can endure while entire generations of galaxies rise and fall around it. This star has seen the first structures of the universe coalesce from the void. It has watched the slow assembly of the Milky Way from the wreckage of smaller protogalaxies. It has survived the era of cosmic reionization and the birth of the first heavy elements. It is a living fossil, a piece of the primordial past that has somehow persisted into the present, challenging us to explain how such a thing could be. The story of HD 140,283 is not just a story of a star, but a story of the human mind grappling with the infinite. It is a narrative of how a single point of light can force an entire species to rethink its place in the timeline of existence. It reminds us that science is not a finished book, but a living, breathing conversation with a universe that is far older, far stranger, and far more complex than we ever dared to believe. In the presence of such ancient light, our own lives are but a single heartbeat, a fleeting flicker in the long, cold night of the cosmos. Yet, we are the only part of this vast machine that has developed the eyes to see the past and the mind to wonder why it is there at all. We stand on our small blue planet, peering through the darkness at a wanderer that shouldn't exist, desperate to hear the secrets it carries from the dawn of time before its light finally fades into the eternal grey of the expanding void. The realization of this star's extraordinary nature began not with a grand revelation, but with the meticulous, almost meditative work of early 20th century astronomers. In an era before digital sensors and silicon brains, the heavens were captured on fragile plates of glass coated in silver nitrate. These pioneers of the night spent their lives peering through brass eyepieces, comparing these glass records year after year, looking for the slightest deviation in the position of the stars. Most of the lights in the sky remained stubbornly fixed, frozen in a silent, eternal choreography that seemed to defy the very concept of motion. But amongst the millions of stationary points, one spark refused to remain still. HD 140,283 did not merely drift. It tore across the celestial sphere with a frantic urgency that shattered the illusion of a static universe. This was the discovery of high, proper motion, a kinematic signature that marked the star as something entirely alien to the local solar neighbourhood. While the Sun and its siblings orbit the centre of the Milky Way in a stately circular procession, this interloper was observed screaming through the void at a staggering velocity of over 1 million miles per hour. Such speed is not merely a physical attribute, it is a historical record. It is the velocity of an object that does not belong to the flat, rotating disk of the galaxy where we reside. Instead, this star is a plunging diver, a guest from the galactic halo, the vast spherical graveyard of ancient suns that surrounds the Milky Way like a ghostly shroud. It is passing through our local space like a bullet through a cloud of smoke, its trajectory a straight line that ignores the gravitational consensus of the younger stars around it. The sheer violence of this motion provided the first definitive clue that astronomers were looking at a survivor from a different epoch. In the hierarchy of the heavens, speed is often a proxy for age. The stars of the galactic disk, born from the enriched gas of a maturing galaxy, move in predictable, orderly paths, but the stars of the halo are the remnants of the Milky Way's chaotic infancy. They are the survivors of ancient collisions and gravitational upheavals that took place billions of years before the Earth was even a grain of dust. By measuring the frantic pace of Methuselah against the backdrop of more distant, truly stationary suns, the observers of the 20th century realized they were witnessing a cosmic anomaly. This star was not rotating with the galaxy. It was falling through it, a relic of a time when the Milky Way was still assembling itself from the wreckage of the primordial dark. As the decades progressed and the precision of our measurements increased, the staggering nature of this speed became even more apparent. To move at 1 million miles per hour is to traverse the distance between the Earth and the Moon in a matter of minutes. It is a pace that suggests the star was flung into its current path by forces of immense magnitude, perhaps the gravitational influence of the first massive black holes or the turbulent merging of protogalactic clouds. This kinematic violence serves as a stark contrast to the star's unassuming appearance. It looks like a common subgiant, yet it possesses the kinetic energy of a celestial juggernaut. This discrepancy forced a shift in the scientific narrative. Astronomers began to understand that they were not just looking at a fast-moving light, but at a messenger from the deep past, carrying the kinetic energy of the universe's violent birth. The discovery of this speedster changed the way we perceive the structure of our own galaxy. It revealed that the Milky Way is not a single, cohesive entity, but a palimpsest, a canvas that has been painted over time and again, with the oldest layers still visible beneath the new. Methuselah is a fragment of that original layer, a piece of the first draft of the cosmos. Its flight through the void is a reminder that the space we inhabit is haunted by the ghosts of what came before. Every arc second it claimed across the photographic plates of the early 1900s was a step further away from the modern era, and a step closer to the mysteries of the beginning. The frantic pace of the star was the first crack in the mirror of our understanding, a hint that the timeline we had constructed for the universe might not be as solid as we believed. This high-velocity transit across the sky was the initial thread that, when pulled, began to unravel the entire tapestry of cosmic time. It signalled that this star had a story to tell that was far longer than the history of the Sun. It was a kinematic outlier, a statistical impossibility that demanded explanation. As the 20th century gave way to the 21st, the focus shifted from how fast the star was moving to what it was made of, and more importantly, how long it had been burning. The speed was merely the herald. The true shock was yet to come, hidden within the very atoms of the star's atmosphere, waiting for the next generation of telescopes to unlock a secret that would bring the entire scientific world to a standstill. The ghost was no longer just passing through. It was beginning to speak, and its first words were a challenge to the age of the universe itself. As the dawn of the early 2000s arrived, the scientific world was armed with a new generation of orbital eyes and sophisticated algorithms designed to peer deeper into the life cycles of the suns. Astronomers turned their attention toward HD 140,283 with the intent of finally pinning down its place in history. They measured its temperature with exquisite precision and analysed its luminosity, seeking to determine exactly where it stood on the long road from birth to extinction. When the data was finally processed and the models reached their conclusions, the result was not a mere refinement of previous knowledge, but a bombshell that threatened to level the entire edifice of modern cosmology. The number that emerged from the calculations was 16 billion years. The shockwaves from this discovery rippled through the halls of academia and the observatories of the world like a physical blow. To the uninitiated, 16 billion years might seem like just another incomprehensibly large number, but to a physicist it was a declaration of war against reality. The prevailing consensus, built upon decades of observations of the cosmic microwave background and the expansion of space, firmly placed the age of the entire universe at 13.8 billion years. The discrepancy was not a minor rounding error or a negligible margin of uncertainty. It was a gap of over 2 billion years. In the logical structure of the cosmos, this was a fundamental impossibility. A star cannot be older than the vacuum that contains it. An object cannot exist before the beginning of time. This single point of light drifting through the scales of Libra had effectively become a mathematical ghost that should not exist. The scientific community found itself plunged into a crisis of logic that felt like a house of cards waiting to fall. If the star truly was 16 billion years old, then the Big Bang, the cornerstone of our entire understanding of the universe, was either fundamentally flawed or entirely fictional. If the beginning of everything occurred later than the birth of this specific star, then our maps of time were nothing more than beautiful illusions. Every textbook, every paper on the expansion of the void, and every theory regarding the origin of matter was suddenly under trial, held hostage by the stubborn, pale glow of a single subgent. The tension in the scientific community was palpable, as researchers scrambled to find a flaw in the logic. They checked the distance measurements, they re-examined the spectroscopic data, and they tore apart the stellar evolution models that had served them for generations. Yet, the 16 billion year figure remained stubbornly resilient. It suggested that we were living in a universe that was younger than its own inhabitants, a paradox that defied the very essence of cause and effect. Cosmologists began to wonder if the Hubble constant, the value that determines how fast the universe is growing, was wrong. They questioned if the physics of the early universe contained hidden variables that had accelerated or decelerated time in ways we could not yet perceive. The crisis went beyond mere numbers. It was an existential threat to the narrative of human discovery. We had spent centuries building a coherent story of how the universe began in a hot, dense state and expanded into the cold, structured expanse we see today. We had measured the afterglow of the first light and tracked the growth of galaxies across billions of light years. To have all of that work undone by one unassuming star felt like a betrayal of the scientific method itself. The Methuselah star became a symbol of the unknown, a reminder that the universe is under no obligation to make sense to us. It stood as a silent, glowing defiance of our most cherished certainties. During this period of uncertainty, the Methuselah star was often discussed in hushed tones, as if it were a glitch in the simulation of reality. If the star was correct, the universe was much older than we thought, which would mean our understanding of dark energy and the expansion rate was completely off the mark. If the star was wrong, it meant our understanding of how stars age, the very foundation of astrophysics, was broken. There was no comfortable middle ground. The scientific community was forced to confront the possibility that their entire timeline of the universe was built on a flawed foundation, a realization that brought both terror and a strange, exhilarating sense of wonder. The debate raged in journals and at international conferences, with some calling for a total overhaul of cosmological theory, and others insisting that the error must lie within the star itself. Yet, as they looked closer at the light of HD 140,283, the mystery only deepened. The star's chemical purity and its physical state as a subgent, a star just beginning to run out of hydrogen in its core, made it a nearly perfect clock. It was as if the universe had intentionally placed a puzzle in the sky that was impossible to solve with the tools at hand. This single point of light threatened to overwrite the history of everything we knew. It forced a generation of thinkers to look into the abyss of the unknown and admit that they might be fundamentally wrong about the age of the world. The Methuselah star was no longer just a fast-moving visitor from the halo. It was a cosmic judge, waiting for humanity to catch up to its ancient truth. The quest to resolve this paradox would eventually lead us to the very limits of our technology and the deepest reaches of our understanding of matter. But for that brief, terrifying moment, the star stood alone, older than time, and twice as mysterious. To understand how a single star could challenge the timeline of the cosmos, one must look deep into the heart of the stellar hierarchy. Our own sun is a creature of the modern era, a third-generation star enriched by the deaths of countless predecessors. It is thick with heavy elements, what astronomers call metals, which act like a cosmic glue, influencing how the star breathes and burns. In contrast, the Methuselah star is a primitive relic, a lean and hungry subgent that possesses almost none of the chemical complexity found in younger suns. It is a star stripped to its barest essentials, composed almost entirely of the raw hydrogen and helium that flooded the universe in the wake of the beginning. While the most massive stars of the early universe were profligate giants, consuming their fuel in a blinding million-year frenzy before detonating in spectacular supernovae, the Methuselah star chose a different path. It is a slow-burning ember, a low-mass sun that has managed to endure by husbanding its resources with extreme parsimony. It has survived eons while its larger cousins vanished into the void, their heavy remains scattered to form the planets and the people of the future. This endurance is the key to its role as a cosmic chronometer. Because it burns so slowly, its transition from one stage of a life to the next occurs over billions of years, creating a slow-motion record of its own existence. At this very moment, HD 140,283 is undergoing a profound internal transformation. For the vast majority of its life, it sat upon the main sequence, a stable period where hydrogen fused into helium within the crushing pressures of its core. But that era has come to an end. The hydrogen at the very centre has been exhausted, leaving behind a dormant core of helium ash. As the central fire falters, the star begins to swell. Gravity, no longer held at bay by the outward pressure of intense fusion, causes the layers surrounding the core to contract and heat up. This triggers hydrogen fusion in a thin shell around the dead center, a secondary ignition that pushes the outer envelope of the star outward. This expansion marks the star's entry into the subgiant phase. It is no longer the compact, efficient machine of its youth. It has become slightly larger, slightly cooler, and significantly more luminous. This specific evolutionary state is what makes the star such an effective clock. The transition from the main sequence to the subgiant branch is a fleeting moment in the life of a star, a sharp turn in its journey that is highly sensitive to the initial amount of fuel it possessed and the purity of its composition. By measuring exactly how far the star has moved along this path, astronomers can calculate its age with a precision that would be impossible for a younger, more stable star. The status of a subgiant allows us to peer into the core's history with unique clarity. Because the star is currently rearranging its internal structure, the subtle nuances of its light reveal the conditions of its birth. The lack of heavy metals in its atmosphere means the star is more transparent than our Sun. Its light escapes from deeper within, carrying information about the temperature and density of the layers where the first nuclear reactions took place. It is a living laboratory of primordial physics. We are not just seeing the surface of a star, we are seeing the results of a multi-billion-year experiment in gravity and nuclear fusion. In the grand theatre of the cosmos, the most spectacular events, the collisions of galaxies, the births of black holes, often happen too quickly for us to grasp their full significance. But the Methuselah star offers a different kind of spectacle, the slow, relentless march of time itself. It is a testament to the fact that in the universe, the small and the patient often outlast the great and the violent. This star has survived the era of cosmic reionization, the assembly of the Milky Way, and the birth of our own solar system. It has watched the universe grow cold and dark, yet it continues to glow, a steady and ancient flame that refuses to be extinguished. The internal mechanisms of this subgiant are the gears of a clock that has been ticking since the dawn of light. Every photon that escapes its surface is a heartbeat, a measurement of an age so vast that it dwarfs the entire history of our species. By studying the way it swells and the way its light shifts, we are attempting to read the very first pages of the Book of Time. The star does not lie. Its physical state is an honest reflection of its history. The challenge lies not in the star's honesty, but in our ability to interpret the language of its light. As we looked closer, the chemical fingerprints left behind by the first stars began to reveal a story of a universe that was once a very different place, a place of pure gas and unbridled potential, where the Methuselah star was born to be the ultimate witness. The light of a star is more than a mere glow. It is a coded ledger, a chemical history written in the language of absorption lines. When astronomers disperse the light of HD 140,283 through a prism, they do not see the rich, complex barcode of a modern sun. Instead, they find a hauntingly empty spectrum. In the lexicon of astrophysics, this star is described as metal poor, a term that carries profound implications for its age. To an astronomer, the periodic table is simplified into a binary. There is hydrogen, there is helium, and everything else is a metal. Oxygen, carbon, neon, and iron are all lumped into this single category, representing the chemical impurities that have slowly accumulated in the cosmos over billions of years. Our own sun is a creature of chemical opulence, a third-generation star born into a universe already saturated with the wreckage of previous stellar lives. It is a population 1 star, rich in the heavy elements that allow for the formation of rocky planets, complex organic molecules, and the very iron that carries oxygen through human veins. But the Methuselah star is a pauper by comparison. Its atmosphere contains more than 250 times less iron than our Sun. It is a vessel of the original elements, composed almost entirely of the pristine hydrogen and helium that flooded the void in the immediate wake of the beginning. This extreme lack of heavy elements acts as a cosmic fingerprint, proving that this star was born in a much younger, much simpler universe, a place where the alchemy of the stars had only just begun. To understand the significance of this chemical purity, one must look back to the era before the first stars ignited. In the first few minutes after the Big Bang, the universe was a cooling forge that produced only the lightest nuclei. There was no solid ground, no carbon-based life, and no metallic cores. The cosmos was a vast, dark sea of gas, waiting for gravity to pull the first clouds together. When the very first stars, the legendary Population 3, finally sparked into existence, they were massive, short-lived titans. They lived for only a few million years before detonating in spectacular fashion, forging the very first atoms of carbon, oxygen, and iron in their dying breaths. These explosions seeded the surrounding gas with the first traces of complexity. HD 140,283 was born from one of these lightly polluted clouds. It is a Population 2 star, a member of the second generation that arose while the universe was still in its infancy. Because it contains such a minuscule amount of iron, we know it must have formed before the vast majority of stars had a chance to live and die. It is a relic of a pristine epoch, a living witness to a time when the galaxy was nothing more than a chaotic swirl of gas and dark matter. The absence of metals is not merely a chemical quirk, it is a definitive proof of antiquity. A star cannot lose its metals over time. It is born with a specific chemical signature that remains etched in its atmosphere until the day it dies. This low metallicity serves as a bridge to the primordial forge. By analysing the specific ratios of elements within the Methuselah star, scientists can reconstruct the nature of the very first explosions that occurred in the dark ages of the cosmos. The star acts as a filter, allowing us to see the chemical ghosts of the first suns that ever shone. It tells a story of a universe that was once a blank canvas, where the first strokes of matter were broad and simple. The iron found in its outer layers is not the product of its own internal fusion, which currently only processes hydrogen and helium, but is instead the inherited wealth of the very first ancestors of the stellar lineage. The star is a survivor of an era of cosmic transition. While the massive first-generation suns tore themselves apart, seeding the universe with the materials for future worlds, this low-mass wanderer held onto its original composition, burning its fuel with a steady, patient resolve. It has carried this primordial signature across the vast distances of the Milky Way, surviving the assembly of the galactic disk and the countless cycles of stellar birth and death that followed. It is a physical piece of the early universe that has somehow persisted into the present day, a chemical time capsule that allows us to touch the era of the first light. In the grand narrative of the cosmos, the Methuselah star stands as a reminder that the complexity we see around us is a recent development. For the vast majority of cosmic history, the universe was a much simpler place, dominated by the raw, unrefined elements of the beginning. The star's spectrum is a silent testimony to that simplicity. It is a relic of an alchemy that occurred shortly after the dawn of time, a period when the rules of the universe were still being written in the hearts of the first suns. By reading the fingerprint of its light, we are not just measuring the age of a star, we are measuring the growth of the universe itself, tracking the slow, steady accumulation of the heavy elements that would one day make our own existence possible. The star remains a lonely, ancient flame, a testament to the endurance of the original light in a universe that has since become crowded with the heavy dust of time. Before the first spark ignited, the universe was a cold and sightless expanse of neutral gas, a lightless era known as the Dark Ages. In this silent gloom, gravity worked with slow, inexorable patience, drawing together gargantuan clouds of primordial hydrogen and helium. When these clouds finally reached a critical density, they collapsed inward, their cores igniting with a ferocity that the cosmos has never seen since. These were the Population 3 stars, the firstborn suns of the universe. They were titans of staggering scale, some growing to hundreds of times the mass of our own sun. They were pure, blue-white beacons of incredible intensity, burning with a frantic, desperate energy that could not be sustained. These first giants were the original furnaces of the cosmos. Inside their massive frames, the pressure reached such extremes that the very fabric of the vacuum seemed to groan under the weight of their existence. Here, in the white-hot centres of these pioneers, the first nuclear alchemy took place. hydrogen nuclei were smashed together to form helium, and as the hydrogen was consumed, the stars began to fuse heavier and heavier elements. For the first time in the history of existence, atoms of carbon, oxygen, and neon were forged in the hearts of these blue monsters. They were the architects of complexity, transforming the simple, uniform gas of the Big Bang into the diverse building blocks of a future world. Because of their immense mass, these first stars lived with a profligate disregard for the future. They consumed their vast reserves of fuel in a mere few million years, a fleeting heartbeat in the grand timeline of the universe. When their internal fires could no longer support their massive weight against the crush of gravity, the end came with a violence that redefined the nature of light. Space tore asunder as these giants collapsed and then rebounded in spectacular supernovae. In those final moments, light screamed into the void with such power that a single dying star could outshine an entire protogalaxy. These explosions were the ultimate acts of creation through destruction, as the shockwaves synthesized even heavier elements like iron and gold, flinging them across the lightless reaches of space. The wreckage of these first suns formed a thin, shimmering veil of gas, a mixture of the original primordial elements and the first traces of metallic ash. It was from this slightly polluted medium that the next generation of stars began to coalesce. Amongst this second wave of creation was HD 140,283. While many of its siblings were also massive and destined for short lives, this specific star was born with a modest mass, a small and sturdy vessel that would not succumb to the frantic pace of its predecessors. It was a population 2 star, a child of the first wreckage, inheriting just enough heavy material to mark its lineage but remaining pure enough to endure for eons. As the Methuselah star ignited, it did so in a universe that was still small and crowded. The first galaxies were just beginning to assemble themselves from the chaotic merging of gas clouds and dark matter halos. The star was a witness to the era of rionization, when the intense ultraviolet radiation from its peers began to strip electrons from the neutral hydrogen filling the void, making the universe transparent to light for the first time. It watched as the first grand spirals began to take shape, and as the chaotic, high-energy environment of the early cosmos slowly settled into a more orderly state. It was a survivor of a violent and transformative epoch, a low-mass ember that held its ground while the titans that birthed it vanished into the darkness. This star is a bridge made of plasma and gravity, connecting the era of the first light to the modern world. It carries within it the chemical signature of those first population 3 giants, a record of the very first explosions that ever occurred. While the giants are long gone, their light having faded into the distant reaches of the expanding universe, the Methuselah star remains as a living fossil. It has spent the last 13 billion years drifting through the evolving structure of the Milky Way, a silent observer of the rise and fall of countless stellar generations. It has seen the birth of the Sun, the formation of the Earth, and the emergence of life, all while maintaining the same steady, patient glow it possessed in the aftermath of the first dawn. The endurance of this star is a testament to the power of the small and the persistent, in a universe that often seems defined by its grandest and most violent events. HD 140,283 proves that the most profound stories are often told by those who simply remain. It emerged from the screaming light of the first supernovae to become a steady flame in the long night. As we look upon it today, we are seeing the same light that began its journey when the universe was less than 1 billion years old. It is a piece of the original architecture, a survivor of the furnace of the first stars, continuing to burn as a lonely, ancient sentinel at the edge of our understanding. The universe functions as a grand, inflating sphere, a fabric of space and time that has been stretching outward since the first moment of existence. To understand the age of this vast container, cosmologists observe the light of distant galaxies, noting how their glow shifts toward the red end of the spectrum as they are carried away by the expansion of the void. This motion is not the movement of objects through space, but the growth of space itself. By measuring the rate of this expansion, the speed at which the cosmic balloon is blowing up, it becomes possible to run the film of history in reverse. We watch as the galaxies draw closer together, The cooling gas grows hot and dense once more, and the entire observable heavens shrink toward a single, infinitesimal point of infinite density and heat. This backward journey through time leads to a definitive boundary, a beginning that occurred 13.8 billion years ago. This number is not a mere estimate. It is the cornerstone of modern cosmology, derived from the most precise measurements ever taken of the early universe. The primary evidence for this age is the cosmic microwave background, a faint uniform hiss of radiation that permeates every corner of the sky. This is the afterglow of creation, the first light that was finally able to travel freely through space when the universe had cooled enough for atoms to form. It is a baby picture of the cosmos, captured by orbital observatories that have mapped the tiny fluctuations in its temperature with staggering accuracy. By analysing the patterns within this ancient light, scientists can determine the composition of the universe, the influence of dark matter, and the rate at which space has expanded over the eons. The data from these missions consistently points to the same conclusion. The clock of the universe began ticking 13.8 billion years ago. This provides the absolute limit for everything within the cosmos. No galaxy, no planet, and certainly no star can be older than the space that holds them. The universe is the house, and the stars are the inhabitants. The house must be built before the guests can arrive. Yet, it is here that the light of HD 140,283 creates a profound and unsettling friction. When the initial calculations for the star suggested an age of 16 billion years, it did not just present a local mystery. It challenged the validity of the cosmic microwave background itself. It suggested that our understanding of the very first moments of the Big Bang might be fundamentally incomplete. If the star is older than 13.8 billion years, then the entire model of an expanding universe, the very metaphor of the inflating balloon, begins to tear at the seams. The conflict between the age of the star and the age of the universe represents a battle between two different ways of measuring time. On one side is the macroscopic view, which looks at the largest scales of space and the ancient echoes of the beginning. On the other side is the microscopic view, which looks at the internal nuclear fires and chemical evolution of a single sun. For these two measurements to disagree by over 2 billion years is a crisis of the highest order. It implies that either our understanding of how stars burn is wrong, or our understanding of how the universe expands is flawed. This discrepancy forced cosmologists to re-examine the Hubble constant, the mathematical value that describes the speed of the expansion. If the universe is expanding faster or slower than we believed, its age would shift accordingly. A slower expansion would mean an older universe, perhaps providing enough room for the Methuselah star to exist comfortably within its borders. However, every time scientists refined their measurements of the afterglow of the Big Bang, the 13.8 billion year figure remained stubbornly firm. The container refused to get any older, even as the star within it insisted on its own ancient pedigree. The friction created a sense of unease that permeated the entire field of astrophysics. We found ourselves staring at a star that seemed to be a survivor from a time before time. The Methuselah star became a thorn in the side of every grand theory, a silent witness that refused to align with the consensus of the group. It stood as a reminder that the universe is not required to be simple or consistent with our current level of technology. The afterglow of creation and the light of this ancient subject were telling two different stories of the beginning, and for a long time there was no way to reconcile them. This tension is the engine of scientific progress. It is the gap between what we know and what we see that drives us to build better telescopes and more complex equations. The star HD 140,283 demanded a more rigorous investigation of both the stellar models and the cosmological constants. It pushed us to look closer at the distance to the star, the amount of oxygen in its core, and the invisible forces like dark energy that might be warping our perception of the timeline. The star was not just an object to be catalogued, it was a challenge to be met, a mystery that required us to look deeper into the very nature of reality itself to find the missing seconds, millions, and billions of years that separated the inhabitant from its home. This friction between the age of the star and the age of the container manifests as a profound schism in modern physics known as the Hubble tension. It is a battle of the constants, where two equally valid and highly precise methods of measuring the expansion of the universe yield results that simply refuse to agree. This is not merely a dry exchange of numerical data, it is a collision of realities that threatens to rewrite the fundamental laws governing the void. On one side of the conflict is the path of the early universe, which looks at the cosmic microwave background, the ancient frozen light from the beginning of time. By analysing this afterglow, scientists derive a value for the Hubble constant of approximately 67 km per second per megaparsec. This slower rate of expansion implies a universe that is relatively old, providing a timeline of 13.8 billion years into which the Methuselah star might, with enough adjustment, eventually fit. On the opposing side is the path of the late universe, which measures the distance to modern cosmic milestones. Astronomers look at the pulsing light of Cepheid variables and the cataclysmic bursts of Type 1a supernovae to track how fast galaxies are receding from us today. This method consistently yields a higher value for the Hubble constant, reaching approximately 73 km per second per megaparsec. This faster rate of expansion tells a much more frantic story, one where the universe is significantly younger, perhaps only 13 billion years old. Within this younger reality, the existence of HD 140,283 becomes an absolute impossibility. If the faster expansion rate is correct, the star is not just an anomaly, it is a violation of the laws of nature, a physical object that predates the very existence of space. The Methuselah star sits precisely within this gap of uncertainty, serving as the pivot point for our entire understanding of the cosmos. It is the physical evidence that prevents us from simply choosing the most convenient answer. If we accept the younger age of the universe suggested by modern supernovae, we must admit that our entire model of how stars age is fundamentally broken. If we cling to the older age suggested by the cosmic microwave background, we must explain why the modern universe appears to be flying apart so much faster than it did in its infancy. The star acts as a weight on the scales of justice, forcing cosmologists to confront the possibility that a third hidden factor is at work, something that has altered the expansion rate over the eons. This hidden hand is often identified as dark energy, the mysterious force that permeates the vacuum and drives the acceleration of the universe. The Hubble tension suggests that dark energy may not be a constant, unchanging pressure, but rather a dynamic force that has evolved throughout cosmic history. Perhaps in the early stages of the universe, the expansion was governed by one set of rules, only for the invisible influence of dark energy to kick into a higher gear as the eons passed. If the nature of the void has changed, then our ability to track time backwards to a single point becomes far more complex. The Methuselah star, with its stubborn and ancient light, suggests that the timeline of the universe is not a simple linear progression, but a narrative shaped by invisible actors that we are only beginning to identify. The scientific debate surrounding this tension has become a high-stakes drama, where the reputation of the standard model of cosmology hangs in the balance. Researchers are no longer just looking for a more precise number, they are looking for a new physics that can bridge the gap between the ancient afterglow and the modern stars. Every new measurement of the Hubble constant is scrutinized with a level of intensity that borders on the obsessive, as the scientific community seeks to resolve the paradox of a star that is older than its home. The friction between these two measurements is where the most exciting discoveries are made, in the narrow space where the old laws fail and the new ones have yet to be written. Within this chasm of logic, the Methuselah star remains a silent judge. It does not care about our equations or our tensions. It simply continues to burn, a ball of plasma that has outlasted the very theories we use to describe it. Its existence demands a universe that is large enough and old enough to contain it, and it refuses to be ignored or explained away as a mere error. As we struggle to reconcile the 67 of the early universe with the 73 of the modern day, the star stands as a reminder that the truth is often found in the discrepancies. It is the friction, the tension, and the conflict that tell us we are on the verge of a deeper understanding of the void. The battle of the constants has transformed the Methuselah star from a curious anomaly into a central pillar of cosmological inquiry. It has forced us to reconsider the role of dark energy and the possibility of new particles or forces that operated in the first moments of the Big Bang. The star is a living challenge to the idea that we have solved the mystery of the beginning. It tells us that the universe is far more mysterious and far less predictable than our textbooks suggest. As we look at this single point of light, we are seeing the collision of two different versions of history, and it is our task to find the single, unified truth that allows both the star and the universe to exist in the same reality. The gap where the star resides is not a void of knowledge, but a fertile ground where the next great revolution in our understanding of time and space is currently taking root. The expansion of the cosmos is not a steady, predictable drift, but a process governed by a phantom influence that defies the traditional laws of gravity and motion. This invisible force, known as dark energy, acts as a hidden hand that permeates every cubic inch of the vacuum, exerting a repulsive pressure that pushes galaxies apart with increasing ferocity. For the first several billion years of cosmic history, the gravitational pull of matter, both visible and dark, acted as a brake, slowing the initial outward surge of the Big Bang. But as the universe grew larger and the density of matter thinned, dark energy took command of the void. Approximately 5 or 6 billion years ago, the expansion of space ceased its deceleration and began to accelerate, a transition that fundamentally altered the trajectory of time itself. This acceleration creates a profound veil that masks the true age of the universe. When we look out into the deep reaches of space, we are trying to calculate the duration of a journey based on the current speed of the traveller. If the universe were expanding at a constant rate, the math would be a simple linear progression. The distance to the farthest light divided by its velocity would yield the age of the beginning. However, because dark energy is constantly stepping on the cosmic accelerator, the velocity we measure today is not the velocity of the past. The universe is stretching the very canvas upon which the stars are painted, making it difficult to pin down exactly when the clock started ticking. This non-linear growth means that our estimates of 13.8 billion years are heavily dependent on our understanding of how dark energy has behaved over the eons. The existence of HD 140,283 serves as a stark reminder that our current equations may be missing a vital piece of the physics puzzle. If the Methuselah star truly sits at the very edge of the universe's birth, it suggests that the early expansion might have been far more complex than our standard models allow. Perhaps dark energy was not always the dominant force, or perhaps there were other, even more exotic influences at play during the first billion years, forces like early dark energy or sterile neutrinos that could have warped the expansion rate in ways we are only beginning to theorize. The star is a physical anchor in a sea of theoretical uncertainty, a solid object that demands a timeline long enough to accommodate its slow, patient evolution. This search for the missing piece of the puzzle has led physicists to question if our laws of gravity derived from the brilliant insights of the 20th century are incomplete when applied to the scale of the entire cosmos. We are looking for a ghost in the machine, a fundamental property of space-time that explains why the vacuum possesses its own energy. The mystery of dark energy suggests that the universe is not just a stage where matter performs its dance, but is itself a dynamic participant that can change the rules of the game. This realization forces a shift in how we date the ancient objects of the sky. We cannot simply look at the light of a star in isolation. We must understand the changing nature of the void through which that light has travelled for over 13 billion years. The ferocity with which dark energy pushes against the gravitational consensus creates a universe that is perpetually trying to outrun its own history. As space expands faster and faster, the light from distant galaxies is stretched to such extreme wavelengths that it will eventually become undetectable, leaving our local group of galaxies as a lonely island in an infinite dark ocean. The Methuselah star is a survivor of the era before this acceleration took hold, a relic from a time when the universe was smaller, denser, and more interconnected. Its light has had to fight against the stretching of space for nearly the entire duration of cosmic time, and the fact that it still reaches our telescopes is a testament to the endurance of the original spark. The complexity of this dating process is further compounded by the possibility that dark energy is not a constant value, a cosmological constant, but a field that changes in strength and influence. If the hidden hand has wavered or strengthened at different points in history, then the age of the universe could be older or younger than the 13.8 billion years we currently claim. The Methuselah star, by sitting so uncomfortably close to that limit, acts as a sentinel for this possibility. It suggests that the universe might have had a longer, slower infancy than our microwave background measurements imply. The star is the evidence that the progression of time is not a straight line, but a curve shaped by forces we cannot see and only barely understand. As we investigate these invisible forces, we find ourselves in a landscape where the very definitions of time and distance become fluid. The acceleration of the void is a reminder that we are observers on a moving platform, trying to measure the speed of a receding horizon. The missing piece of the puzzle may not be a new particle or a new star, but a fundamental revision of how we perceive the relationship between energy and the vacuum. The Methuselah star remains at the centre of this investigation, a silent witness to the era when gravity still held sway, and the dark energy that now dominates the sky was merely a whisper in the dark. It challenges us to look beyond the visible and to find the truth in the invisible hand that continues to push the galaxies toward the edge of forever. The resolution of the paradox of the 16-billion-year-old star required an intervention from the most sophisticated instruments ever launched into the heavens. The first major attempt to pin down the distance of HD 140,283 occurred in the late 1980s and early 1990s with the European Space Agency's Hippocos satellite. This mission was a pioneer in the field of astrometry, designed to measure the positions and motions of stars with a precision that was impossible from beneath the blurring veil of the Earth's atmosphere. Hippocos utilized the principle of parallax, the slight, apparent shift of a nearby star against the backdrop of more distant stationary objects as the Earth completes its orbit around the Sun. By measuring this tiny angle from two different points in the Earth's journey, astronomers could use basic trigonometry to calculate the distance to the star. However, even with the vantage point of space, the measurements provided by Hippocos were fraught with a subtle but devastating margin of error. The distance it calculated for the Methuselah star was just slightly too short. In the delicate math of stellar evolution, distance is the master variable. If a star is thought to be closer than it actually is, its observed light is interpreted as coming from a less powerful source. This led scientists to believe the star was inherently dimmer, a conclusion that forced their models to assign it an impossibly ancient age. A dimmer subgiant is a star that has been burning its fuel for a longer duration, and it was this miscalculation that produced the terrifying figure of 16 billion years, setting the star at odds with the very birth of the universe. To correct this distortion, the scientific community turned to the Hubble Space Telescope, an observatory capable of surgical accuracy. Between 2003 and 2011, astronomers used Hubble's fine guidance sensors to revisit the parallax of the Methuselah star. These sensors are so precise, they can measure an angle equivalent to the width of a human hair seen from several miles away. By observing the star at 6-month intervals over several years, Hubble was able to refine the measurement of its cosmic shift with unprecedented clarity. The results were transformative. Hubble proved that the star was actually slightly further away than the Hippocos data had suggested. This change in distance, though seemingly small, had a profound impact on the star's biography. Because the star was further away, its intrinsic brightness, its true luminosity, had to be higher for it to appear as it does in our sky. In the world of astrophysics, a brighter star is a star that is either more massive or further along in its life cycle than previously suspected. When this new, higher luminosity was plugged into the revised stellar models, the estimated age of the star began to tumble. It fell from 16 billion years to 14.5 billion years. While this was a massive leap toward reconciliation, it did not entirely solve the mystery. 14.5 billion years is still older than the 13.8 billion year age of the universe, but it brought the two figures into a range where the margin of error could finally begin to bridge the gap. The use of parallax by the Hubble Space Telescope was a triumph of geometry over uncertainty. It allowed us to place the Methuselah star more accurately within the three-dimensional map of our galaxy, providing a firmer foundation for every other calculation that followed. This was not just a correction of a number, it was a refinement of our vision. By knowing exactly where the star stood in the void, we could better understand the temperature of its core and the rate at which it was consuming its remaining hydrogen. The impossible age was revealed to be a product of our own limited perspective, a reminder that in the study of the infinite, the smallest error in distance can lead to a massive distortion in time. The Hubble intervention demonstrated that the crisis of the Methuselah star was, at its heart, a crisis of measurement. It showed that the star was not a supernatural entity defying the laws of physics, but a physical object that required the most exacting standards of observation to be understood. The downward revision of its age was a relief to cosmologists, yet the new figure of 14.5 billion years remained uncomfortably close to the edge of the beginning. It left a window of only a few 100 million years for the first stars to form, leave, and die, and for the Methuselah star to coalesce from their wreckage. The pressure was now on the astrophysicists to look even deeper into the star itself, not just at its distance or its brightness, but at its very chemistry. This period of refinement was a testament to the self-correcting nature of science. When faced with a paradox that threatened to upend our entire understanding of the cosmos, the answer was not to abandon the theory of the Big Bang, but to build a better yardstick. The Hubble Space Telescope provided that yardstick, stripping away the layers of uncertainty and bringing the ancient wanderer back from the realm of the impossible. The star was no longer a ghost from before the beginning of time, it was a survivor that sat at the very limit of what was possible. The quest then shifted to the subtle influence of oxygen and other elements within the star's heart, a final attempt to find the missing millions of years that would finally allow the oldest star in the universe to exist in perfect, logical harmony. The final resolution of the star's impossible age lay not just in the vast distances of space, but within the microscopic dance of atoms inside its burning heart. While the measurement of distance had brought the age down from the realm of the supernatural, there remained a stubborn discrepancy that only the most precise chemical analysis could resolve. The key was oxygen. In the specialized language of stellar evolution, the ratio of oxygen to other elements acts as a secret throttle for a star's internal clock. For years, models of HD 140,283 had assumed a standard chemical profile, but when astronomers utilized high-resolution spectroscopy to peer into the star's atmosphere, they discovered a surprising abundance of this vital element. This discovery of higher oxygen levels than previously predicted was the final lever needed to move the mountain of time. Oxygen is not merely a passive bystander in the life of a star, it is a fundamental driver of the rate at which a subgiant evolves. In the lean, metal-poor environment of the early universe, an increased presence of oxygen alters the opacity of the stellar material and influences the efficiency of nuclear burning. By discovering that the Methuselah star was richer in oxygen than its iron content suggested, astrophysicists realized that the star had reached its current evolutionary stage much faster than their earlier, simpler models had allowed. This chemical revelation allowed them to shave hundreds of millions and eventually billions of years off the estimate. The revised age that emerged from this synthesis of distance and chemistry was 14.5 billion years. At first glance, this figure still appears to be a violation of the 13.8 billion year limit of the universe. However, in the world of high-precision science, no number stands alone. It is always accompanied by a margin of error. For the Methuselah star, that margin was determined to be approximately 800 million years. This is the cushion of uncertainty that arises from the limits of our telescopes and the complexities of our stellar models. When this margin is applied, the age of the star shifts from a single, impossible point into a range of possibilities. It is here that we find a precarious alignment with the dawn of existence. If one subtracts the 800 million year uncertainty from the 14.5 billion year estimate, the star's age drops to 13.7 billion years. This is a narrow, breathtaking window that sits just 100 million years after the Big Bang itself. It is a tightrope walk across the abyss of time. The star still sits uncomfortably close to the edge of the beginning, leaving almost no room for further error. It suggests a universe that was incredibly efficient at its inception, capable of cooling the fires of creation and condensing the first clouds of gas into long-lived stars in what is, on a cosmic scale, a mere blink of an eye. This narrow margin represents a victory for the scientific method, yet it remains a source of lingering tension. To accept this alignment is to accept that the Methuselah star formed almost immediately after the first generation of massive giants exploded. It requires a timeline where the transition from the chaos of the Big Bang to the birth of structured, low-mass stars happened with localized ferocity. The star is no longer a paradox, but it remains an extreme outlier, a physical object that tests the very limits of our cosmological framework. It is as if the universe is holding its breath, with the star's age and the universe's age pressed together so tightly that there is no space left for a single mistake in our logic. The journey from 16 billion years down to 14.5 billion and finally into the overlap of the 13.8 billion year limit is a testament to our persistent pursuit of the truth. We have used the most advanced orbital observatories and the most complex nuclear physics to bring this ancient wanderer into the fold of reality. Yet, the fact that it sits so close to the boundary of the beginning is a reminder of how little we still truly understand about the first moments of time. The tightrope walk of the Methuselah star is a reflection of our own struggle to map the infinite. We have found a way for the star to exist, but in doing so, we have discovered just how thin the ice is upon which our understanding of the early universe rests. This precarious alignment does not diminish the mystery of the star, rather, it focuses it. We are no longer asking if the star is a ghost, but how it managed to emerge so quickly from the primordial fog. It stands as a sentinel at the very gates of time, a witness to the transition from a universe of pure energy to a universe of matter and light. The 800 million year margin of error is the only thing that prevents a total collapse of our cosmological model, a fragile bridge of probability that allows the oldest thing we can see to reside within the oldest thing we can measure. As we continue to refine our instruments, that bridge may widen, or it may narrow even further, keeping us forever on the edge of a new and perhaps even more startling revelation about the nature of the beginning. The future of HD 140,283 is as certain as its past is mysterious. Having survived the tumultuous birth of the cosmos and the slow assembly of the Milky Way, this ancient wanderer is now approaching the final chapters of its long, luminous life. The subgiant phase, which has allowed us to peer so deeply into its history, is a fleeting transition in the grander timeline of a star. Eventually, the hydrogen shell surrounding its dormant core will be exhausted, and the star will be forced to confront the inexorable pull of its own gravity once more. The core will contract and heat to even more extreme temperatures, causing the outer envelope of the star to bloat outward into a red giant. In this stage, the pale, unassuming spark will swell to a size that dwarfs its current form, its light shifting toward a deeper, more somber crimson as it radiates its remaining energy into the widening void. This final expansion is the last gasp of a titan that has outlasted nearly everything else in the sky. Once the red giant phase concludes, the star will gently shed its outer layers, casting a shimmering shroud of gas into the interstellar medium, a final gift of recycled material to the galaxy it has traversed for eons. What remains will be a white dwarf, a dense, cooling ember no larger than the Earth, but containing the mass of a sun. This white dwarf will no longer be powered by the fires of nuclear fusion. It will shine only with the residual heat of its ancient life. It will become a cosmic diamond, a crystalline relic of the beginning of time, cooling with such agonizing slowness that it will continue to glow for trillions of years. As a white dwarf, the Methuselah star will become the ultimate witness to the end of all things. It will endure long after our own sun has withered and died, long after the spiral arms of the Milky Way have dissolved into a chaotic swarm of aging stars, and perhaps even long after the last galaxies have drifted beyond the horizon of the observable universe. It is a bridge that spans the entire history of the cosmos, connecting the chaotic, high-energy aftermath of the Big Bang to the cold, dark, and lonely future of the heat death. It has seen the first light break through the primordial fog and it will likely be there to see the last light fade into the eternal grey of entropy. It is a living fossil that has successfully navigated the hazards of a violent universe to become a silent sentinel of the void. The significance of this star, however, reaches far beyond its physical endurance or its chemical purity. It serves as a mirror reflecting the remarkable nature of the human observer. We reside on a small blue planet orbiting a middle-aged sun, a world that is a relative newcomer to the cosmic stage. Yet, in the brief window of our existence, we have developed the eyes to see this ancient light and the minds to wonder why it exists at all. We have built great glass mirrors to catch photons that began their journey before the Earth was even a thought, and we have devised complex mathematical languages to decode the secrets hidden within those pulses of energy. We are the only part of the universe that has developed the capacity to look back at its own ancestors and ask where it came from. There is a profound humility in the presence of such ancient light. Our lives, our civilizations, and even the entire history of our species are but a single, fleeting heartbeat in the multi-billion-year narrative of HD 140,283. Yet, it is through our curiosity and our relentless desire for truth that the star finds its meaning. Without an observer to measure its speed, analyze its spectrum, and marvel at its age, the star would be nothing more than a ball of plasma drifting through a sightless dark. We are the consciousness of the cosmos, the mechanism by which the universe attempts to understand itself. We are the children of the stars, looking back through the telescope of time to understand our grandparents before the lights of the universe finally go out. The Methuselah star reminds us that science is not a finished book of facts, but a living, breathing conversation with the infinite. It teaches us that every paradox is an invitation to look deeper, and every discrepancy is a signpost toward a more profound truth. As we continue to refine our understanding of dark energy, the Hubble constant, and the first moments of the Big Bang, the star will remain there, a steady and ancient flame at the edge of Libra. It is a testament to the fact that the universe is far older, far stranger, and far more beautiful than we ever dared to imagine. In the end, when the last of the stars have faded and the galaxies have all disappeared into the dark, the story of the Methuselah star will be the story of the universe itself, a journey from heat to cold, from light to shadow, and from simplicity to complexity. It is a journey that we have been privileged to witness, if only for a moment. As we turn our gaze away from the telescope and back toward our own fragile world, we carry with us the knowledge that we are part of a narrative that is 14.5 billion years in the making. We are the inheritors of the original spark, the descendants of the first suns, and the only ones who can tell the story of the ancient wanderer that arrived at the party before the house was even built. The light of the Methuselah star is a gift from the dawn of time, a reminder that even in the face of the eternal dark, the fire of discovery continues to burn bright.